Welcome everyone. I am Dr. Prashant Kumar Jaina, Assistant Professor in the Department of Electrical and Electronics Engineering. Today we are going to see an important topic in electrical engineering, that is the testing of relays, which is one of the important area in our industrial operations or to satisfy the objectives of our electricity network. So whether you are an undergraduate student, a practicing engineer or someone working in the industry, understanding the function, types and testing of relays is very crucial for ensuring the reliability and safety of electrical systems. We see relays are the unsung heroes of the electrical world, quietly ensuring that the power system functions safely and efficiently. They are critical components in various applications, from simple household appliances to complex industrial power grids. The primary function of a relay is to act just like a switch or to control the flow of electricity based on specific conditions. Given their crucial role, relay testing becomes indispensable in maintaining the safety, reliability and performance of electrical systems. So, in this lecture, we will provide an in-depth exploration of relay testing, delving into the types of relays, their applications, testing methodologies, the mathematical formula, industrial practices and the future of relay testing. So, we will see first the types of relays and their application. Relays come in variety types, each designed to perform specific functions. Understanding the different types of relay and their application is essential for an engineer tasked with testing and maintaining these devices. So, first one we will see electromechanical relays. So, electromechanical relays are the most traditional type of relays operating through a mechanical movement triggered by an electromagnetic coil. When the coil is energized, it creates a magnetic field that attracts a movable armature, causing the contacts to open or close. These relays are widely used in industrial control systems, automotive electronics and home appliances. They are preferred in applications where simplicity, reliability and the cost effectiveness are prioritized. So, what are the testing considerations here? These relays require functional testing to ensure that the mechanical movement of the contacts is smooth and free from wear and tear. Timing tests are also crucial to verify that the relay responds within the required time frame or not. Next, we will see the solid state relays, SSR. So, these solid state relays use semiconductor components to perform switching operations without any moving parts. They offer faster switching times, longer lifespans and are more resistant to shock and vibration compared to EMRs. The solid state relays are commonly used in applications requiring high speed switching such as industrial automation, heating control and motor drives. The testing of these relays focus on verifying the integrity of the semiconductor components. Dielectric and thermal testing are crucial in this case to ensure the relay can handle the required voltage and current levels without overheating. Next, we see protective relays. So, protective relays are designed to detect faults in power systems and initiate the disconnection of the faulty section to protect the rest of the network. They are highly specialized and can be categorized further into overcurrent relays, differential relays, distance relays and more. So, the protective relays are essential in case of power generation, transmission and distribution systems. They ensure safe and reliable operation of electrical grids by isolating the faults and preventing widespread outages. Now, what are the testing considerations here? These relays undergo rigorous testing including functional, timing and impulse voltage tests. These tests ensure that the relay operates correctly under fault conditions and meets industrial standards such as our IEC 61850. Next, reed relays. Reed relays consist of reed switches encased in a sealed glass tube. When an external magnetic field is applied, the reed moves to open or close the circuit. Reed relays are known for their fast response time as well as high sensitivity. So, these relays are basically used in our telecommunications, testing equipments and low voltage signal switching applications. Their ability to operate in harsh environment makes them ideal for aerospace and military applications. So, what are the testing considerations here? These relays require testing for contact resistance, timing and magnetic sensitivity. So, ensuring the relay operates correctly in response to specific magnetic field strength is very crucial in such type of conditions, such relays. Next, we will see the time delay relays. This time delay relays introduce a delay between the activation of the relay and the opening or close of the contacts. They are used to control sequence of operations, providing a delay in circuit activation or deactivation. These relays are used in our industrial automation, lightning control and motor startup applications where specific timing sequences are required. So, what are the testing considerations we do here? These relays involve verifying the accuracy of the delay setting and ensuring consistent performance over multiple cycles. Next, we will see latching relays. The latching relays maintain their position after being actuated without the need for continuous power. They can remain in the set or reset position until and unless an opposition force is applied. So, these relays are used in memory circuits where it is essential to retain the state of a circuit without continuous power, such as in the safety interlock systems and alarm systems. The testing considerations in this case is these relays focus on ability to maintain the state without power and verifying that the relay reliably switches between the states when actuated. So, what is the necessity of our relay testing? Why we are going for it? So, we will see the several reasons for which the relay testing has been very critical. So, first reason is our assurance of safety. Relays are integral to protecting electrical systems from faults, short circuits and as well as overloads. Testing here ensures that the relay operate correctly, which will prevent the accident and minimize the risk of equipment damage. Second necessity is that the verification of the reliability. Regular testing verifies that relays will function as expected during fault conditions. This is particularly important in critical system where relay failure could lead to a catastrophic consequences. Next, we will see the compliance with standards. So, relays must comply with specific industry standards such as those set by International Electrotechnical Commission, that otherwise known as IEC, or the Institute of Electrical and Electronics Engineers, that is known as IEEE. So, the testing will ensure that the relays meet the standards, which is crucial for system certifications and regulatory approvals. Next is that performance optimization. So, over time relays may degrade due to environmental factors, wear and tear or aging. So, testing can identify these issues, allowing for timely maintenance, recalibration or replacement to optimize performance. So, preventive maintenance. Testing relays as part of a preventive maintenance program, it will help to detect potential issues before they lead to failures. This proactive approach can extend the lifespan of relays and will reduce the downtime. So, we will see what are the different types of relay testing. So, relay testing can be categorized into several types, each designed to assess different aspects of relay performance. First is functional testing. Here the objective is to verify that the relay operates according to its design consideration or specifications. So, what is the procedure here? So, functional testing involves applying the specified input signals to the relay and observing the output. This test checks whether the relay correctly opens or closes its contact in response to the input conditions. The applications here is that this functional testing is applicable to all types of relays and is typically the first test conducted during the testing process. So, for example, in a protective relay, functional testing might involve simulating a faulty condition and verifying that the relay initiates the correct protective action such as tripping a circuit breaker. Next we will see the dielectric testing. It is done to ensure that the relay's insulation can withstand operating voltages without any breakdown. This test involves applying high voltage across the relay's insulation for a specified duration. The test checks for insulation breakdown or excessive leakage current, which could indicate a potential failure. This testing is particularly important for relays used in high voltage application such as protective relays in power systems. So, for example, a dielectric test on high voltage relay might involve applying a voltage of 2 kilovolt across the insulation for 1 minute and measuring the leakage current. If the current exceeds the specified limit, the relay may fail the test. Next we go for the timing test. This is done to measure the time it takes for the relay to respond to a fault condition. This involves applying a fault condition to the relay and recording the time it takes for the relay to operate. The response time is compared to the relay specifications to ensure it meets the required performance. These tests are crucial for protective relays where timely operation is essential to prevent damage to the electrical system. So, in an overcurrent relay, a timing test might involve applying a current equal to our 150% of the relay's pickup current and measuring the time it takes for the relay to trip. So, the measured time is then compared to the relay's time current characteristics curve. Next comes our contact resistance testing. So, this is done to assess the resistance of the relay contacts, which can affect the relay's ability to conduct current effectively. This testing involves passing a small current through the relay contacts and measuring the voltage drop. The resistance is calculated using our Ohm's law and the result is compared to the relay specification here. This is done for all relays, especially those used in high current applications where our contact resistance can lead to a significant power loss. For example, if you see a contact resistance test on an industrial relay, it might involve passing a 1 ampere current through the contacts and measuring a voltage drop of let in 10 millivolt. So, the calculated resistance is 10 milliohm and it is then compared to the allowable limit. Next we see the thermal testing. So, this is done to evaluate the relay's performance under various temperature conditions while ensuring it can operate reliably in different environmental conditions. This involves subjecting the relay to different temperature conditions from extreme cold to extreme heat and observing its performance. So, the relay's operation is monitored to ensure it functions correctly across the specified temperature range. So, for application is that thermal testing is particularly important for relays that are used in environments with significant temperature variations such as outdoor installations or industrial processes. So, thermal test on a relay might involve placing the relay in a temperature chamber, setting to for the let me minus 40 degree centigrade, operating the relay, then gradually increasing the temperature to let 80 degree centigrade and observe its performance. Like this we have to perform this. Next hour comes mechanical endurance testing. This is done to assess the mechanical durability of the relay over repeated operations. So, mechanical endurance testing involves operating the relay continuously for a specified number of cycles, for example 10,000, 1 lakh operations, and observe any signs of mechanical wear, degradation or failure. This mechanical endurance testing is important for relays in applications with frequent switching such as motor control relays or lighting control systems. So, mechanical endurance test might involve actuating a relay 1 lakh times and checking for any changes in contact resistance, timing or functional performance. So, we will see some of the mathematical formula in relay testing we do. So, mathematics is integral to relay testing, particularly in analyzing timing, current and fault conditions. So, some of the key mathematical formula used in relay testing are, first one is our Ohm's law, that is we discuss generally all of you know Ohm's law is V is equal to IR. So, this is a fundamental in the electrical engineering relating to voltage, current and resistance. So, in relay testing this equation is used to calculate the expected behavior of the relay under various conditions. This is used in contact resistance testing where our voltage drop across the relay contacts is measured and the contact resistance is calculated just we did before. This will ensure the relay can conduct current effectively. So, for example, consider a relay contact where a current of 2 ampere is passed through and measured voltage drop of 0.05 volt. So, what is the using Ohm's law you can calculate that R is equal to V by I, you do it, you will get that R is will be equal to 0.025 ohms. So, this contact resistance is then compared to the specified limit to determine if the relay passes the test or not. Next our power equation P is equal to V into I, power is equal to voltage into current. So, the power equations relates the electrical power to the voltage and the current. This equation is crucial in assessing the power handling capabilities of the relay during testing. During thermal what is the application here? During thermal testing, the power equation is used to calculate the amount of power dissipated by the relay and assess its ability to handle this power without overheating. For calculation we see an example, if a relay carries a current of 10 ampere with a voltage drop of 0.1 volt across its contacts, the power dissipated is, this power dissipation helps to determine if the relay can operate without excessive heating or not. So, power we can get V into I is equal to 1 watt, time current characteristics curve. Here the formula is the T is equal to K divided by I by I pickup power n minus 1. This equation describes the time current characteristics of a relay, where T is our operating time, I is the fault current, I pickup is the pickup current, and K is a constant and n is an exponent that varies based on the type of relay. So, the time current characteristics curve is used in timing tests to determine whether the relay operates within the required time under different fault conditions. So, the curve helps to ensure that the relay provides adequate protection without unnecessary delay. For example, we see that if you consider an overcurrent relay with a pickup current of, let I pickup is equal to 5 ampere and fault current I is equal to 10 ampere, constant K is equal to 1 and exponent n is equal to 2. So, the operating time is calculated to be T is equal to 0.33 seconds. So, this time is then compared to the relay's specification to ensure that it meets the required performance. Next is our impulse voltage equation. The formula here is that impulse voltage V imp is equal to V naught e power minus t by tau. This equation describes the behavior of the impulse voltage during the dielectric testing. The V impulse is the impulse voltage, V naught is the initial voltage and t is the time and tau is the time constant of the circuit. So, impulse voltage testing is conducted to simulate lightning strikes or other high voltage transients that a relay might encounter. So, the equation helps in assessing the relay's ability to withstand these impulses without any insulation breakdown. So, impulse voltage testing, next for the impulse voltage testing we can see one example, let us see. So, suppose a relay is subjected to an initial impulse voltage of V naught is equal to 5000 volts with a time constant tau is equal to 10 millisecond. The impulse voltage after 5 millisecond is calculated to be, you apply the formula, we will get that it will be nearly equal to 3032.5 volts. So, this calculation will help to determine if the relay can understand the transient voltage without failure or not. Next we will see some industrial practices that we use in our relay testing. So, industries have developed various practices to ensure the accuracy, efficiency and reliability of our relay testing. These practices are designed to meet industry standards, reduce testing time and ensure the long term performance of the relay. So, first is our automated testing. This automatic relay testing, it involves using specialized testing equipment that can perform multiple tests simultaneously, reducing the time required for testing and increasing the accuracy. This reduces the human error, it will ensure the consistency and it will allow for testing of a large number of relays in a shorter period. It is particularly beneficial in manufacturing environments where relays are produced in large quantities. Next, our on-site testing. So, on-site testing involves testing of the relays in the field where they are installed and operating. This ensures that the relay is functioning correctly in its actual operating environment. This can identify issues that might not be apparent in a controlled laboratory environment, such as those that are caused by the environmental factors or installation factors. For example, in a power substation, on-site testing of protective relays might involve simulating fault conditions and verifying that the relays correctly isolate the faulty section of the network or not. Next is our periodic testing. The periodic testing involves regularly testing relays as part of a preventive maintenance program. This helps to detect potential issues before they lead to relay failure. This extends the lifespan of relays, reduces the risks of unexpected failures and ensures continued compliance with industry standards. So, a utility company might schedule periodic testing of all protective relays in its transmission network in every 1 year, 2 years, like as per their convenience. So, this testing would include functional, dielectric and timing tests to ensure that relays are operating correctly. Next, data logging and analysis. So, advanced testing systems often include data logging features that record the results of each test. This data can be analyzed to identify trends, predict potential failures and optimize the relay settings. So, data logging allows engineers to track the performance of relays over time, identify degradation of wear and make informed decision about the maintenance environment. For next we will see some case studies in relay testing. First one will see one improving relay performance in a power plant. So, a power plant experienced frequent tripping of relays during normal operation, leading to unplanned shutdowns and significant financial losses. So, what happened? In the testing approach, a detailed relay testing procedure was initiated involving functional, timing and thermal tests. The tests revealed that the relays were overly sensitive to minor fluctuations in current, which caused nuisance in tripping. So, what are the solutions they found? The relay settings were recalibrated based on the timing test results and additional thermal testing was conducted to ensure the relays could handle the operating conditions without false tripping. So, the outcome was that the plant successfully reduced the nuisance tripping by 90%, that lead to improved reliability and reduced downtime. Next, we will see the future trends in relay testing. So, as electrical systems continue to evolve, so too does the field of relay testing also. So, some of the emerging trends include that first is very common, that the integration of Internet of Things. So, relays in smart grids and industrial systems are increasingly being equipped with IoT capabilities, allowing for real time monitoring and remote testing. So, the benefits here is that the IoT integration enables continuously monitoring of relay performance and allow for early detection and potential issues and reduce the need for manual testing. Next, artificial intelligence in testing. So, artificial intelligence algorithms are being developed to analyze testing data, predict potential failures and optimize relay settings dynamically. So, this can process large volumes of data from multiple relays, identify the patterns and trends that human operators might miss. So, this can lead to more accurate predictions of relay failure and more efficient maintenance schedules. So, an AI system might analyze data from thousands of relays in a power grid and identify that relays in a particular region are showing signs of wear earlier than expected. So, the system could then recommend adjustments to the maintenance schedule or relay settings to prevent such failures. Next, virtual testing environments. So, digital twins and simulation models are being used to test relay operations under a wide range of scenarios without the need for physical relays. So, virtual testing will allow for simulation of extreme conditions such as rare fault scenarios or unusual environmental factors without the risk of damaging to the physical layer. So, a utility company might use a digital twin of its power grid to simulate the impact of a major storm on relay performance. So, the simulation could help to identify potential vulnerabilities and guide improvements to relay settings and maintenance practice. So, in conclusion, we will see that the relay testing is a cornerstone of electrical engineering, ensuring the safety, reliability and efficiency of our electrical systems. So, by employing a combination of traditional testing methods and modern technologies, engineers can maintain high standards of performance in relays. So, this content has provided a comprehensive overview of relay testing including the different types of relay, their application, testing methodology, some mathematical formula, some industrial practices and our future trends. So, as the electricity industry continues to advance, the testing will remain a dynamic and evolving field. So, as we discussed before, the integration of IoT, AI and virtual testing environment represents the next frontier in relay testing, offering new opportunities to enhance the accuracy, efficiency and reliability for this critical process. Whether in power generation, industrial automation or telecommunications, the principles and practices of relay testing will continue to play a vital role in ensuring the safe and effective operation of our electric systems worldwide. Thank you for attending the lecture.